Good morning, children. This is 12th Physics, Unit 3, Magnetic Effects of Current and Magnetism. Chapter 6, Electromagnetic Induction. So, we have learnt about electromagnetic induction. We know that magnetic field is produced around a current carrying conductor. That is the phenomena of, but children, is electric current also produced from magnetic field? Yes, it is produced. So this was proved by the Faraday and Henry's experiment that proved that when a coil is placed in a changing magnetic field, it produced electric current. So children, the reverse is also true. So let's start with first magnetic flux. So children, when we place an object or a plane in magnetic field, so this is our plane we have placed in the magnetic field, then we know that the number of magnetic lines will pass through the object. These number of magnetic lines which are passing through the object, they can be described in terms of magnetic flux. Now, in order to define magnetic flux, first we will see that the magnetic flux, it depends upon which factors. So children, the magnitude of magnetic flux, firstly, it depends upon the magnitude of external magnetic field. So children, more is the magnetic field, more is the strength of magnetic field, more will be the number of magnetic field lines. And so more will be the number of magnetic field lines passing through a particular area. So flux depends upon the magnitude of external magnetic field. Secondly, flux depends upon the area through which the magnetic field lines are passing. So more is the area, more will be the flux passing through it, right? Now children, let us consider two different situations. Here you can see that the plane is kept perpendicular, or the plane or the area vector and the magnetic field, they are along the same direction, or the plane is kept perpendicular to magnetic field. So here if you see children, the area vector, that is the vector which is perpendicularly outward from the surface, that is represented by n cap, that is the area vector, right? Now here the number of magnetic field lines that will be passing through this area will be maximum. Yes, right? And here the angle between the magnetic flux, magnetic field B and area vector N is 0 because they are along the same direction. They are parallel to each other, right? In the second case, we are placing the plane along the magnetic field, right? Here the area vector is in this direction. So the angle between the magnetic field B and the area vector n cap is 90 degree. And in this case, children, what do you think? How many field lines are going to pass? No, minimum 0. So here the flux will be 0. So children, here you can see that the flux, it is depending upon the angle between the area vector and the magnetic field. So as we know that cos 0 is 0 and cos 90 is 1, it means it depends upon the cos function, right? So the third factor on which the magnetic flux depends is your cos theta. So if we combine all these, we will get phi is proportional to BA cos theta. And if we remove proportionality sign, a constant will appear, and in say SI units, the constant value will be 1. So you will get phi equals to BA cos theta. Cos theta, we know it's dot product, so it would be B dot A. So phi equals to B dot A, which is equals to BA cos theta. This is for plane uniform surface, right? Now, children, if we have a non-uniform surface, it is of just irregular shape. This is of regular shape, right? This now, if we move towards an irregular shaped object, and if we need to calculate the flux through it, then it will be calculated with the help of the line integral, right, over the surface. So phi will be equal to the surface integral B dot dA. Okay, children. So how you can define magnetic flux? Magnetic flux can be defined as it is the total number of magnetic field lines which are crossing through the particular area normally. Okay, so that is your magnetic flux. Now children, magnetic flux is a scalar quantity. That is, it does not have direction, but it can be positive or negative. So suppose this is an object through which the magnetic field lines are passing. Now if you see the left surface of the object, then you see the magnetic field lines are entering through the left surface and they are leaving through the right surface of the object. Now let us consider a very small, here you can see a very small surface element. We have considered a small element, that is dA, on the left surface of the object. Then the area vector will be along this, that is n cap. Then the angle between the magnetic field B and the area vector n cap, this angle will be greater than 90. And we know if the angle is greater than 90, then cos of that will be negative. So your d phi, that is the magnetic flux, will be negative for this, for the theta greater than 90. Right. Now let's move towards the small element. We are going to suppose here the small element dA on the right surface of the object, and suppose and the area vector will be in this direction, right? Now here the angle between the magnetic field B and the area vector n will be less than 90, and we know the cos for the angle less than 90 is always positive. So your d phi, that is flux, will be positive. So children, we can summarize that the flux, the magnetic field lines, when they are coming in inside flux, will be negative, and the magnetic flux outside will be positive. So magnetic flux is a scalar quantity. It does not have any direction, but it can be positive or negative. So magnetic flux phi is equal to B dot A, that is BA cos theta. This is for one turn. This is for one coil. Suppose we are having a number of turns, right? We are having a number of turns of the coil. Suppose the number of turns of the coil are n. Then the total magnetic flux will become n times. So that is n BA cos theta. Right, it would be n BA cos theta, and this we know that if the theta value is 90, then flux will be 0. This we already saw in the previous slide. And if the angle theta is 0, then the flux will be maximum, that is BA. Right, children? Now let's talk about electromagnetic induction. So we have already done in this in class 10, that is, it is the process of producing current and EMF. How, what change you are doing? We are changing the magnetic field, we are changing the magnetic flux, right? So the process of production of generation of current or EMF by changing the magnetic field is called electromagnetic induction. And because of electromagnetic induction, the EMF that is produced is called induced EMF, and the current, suppose it is a closed circuit, आपने wire से करके उसको closed circuit बना दिया, तो उस induced EMF की वजह से current flow होगा, and that current is the induced current. So this Electromagnetic induction is used in our day-to-day appliances. That is, it is used in the power generators, dynamos, transformers, etc. Next, children, the SI unit of magnetic flux is Weber, or you can say Tesla per meter square. And as we know, it is a scalar quantity, and the outward flux is positive, and the inward flux is taken to be as negative. Now, uh, Faraday and Henry, they performed a number of experiments, right? Let's talk about experiment 1. So in experiment 1, here children, what we are having, here this is a coil C. Now the coil C is connected to a galvanometer over here. This is G is your galvanometer. Here galvanometer's work is to detect the current. So as shown in the figure, what we are doing, we are here we are having a coil which is having a number of turns. So here we are bringing the north pole of a bar magnet is pushed towards the coil. So what do we see? It was seen that the galvanometer showed a momentary deflection. Right? एक बार deflect हुई, right? It indicates that current is produced in the coil because of the movement of the bar magnet. Right? Next, when the bar magnet, when we had brought the north pole of the bar magnet towards the coil, when we had made it stationary, when we stopped its motion, as the motion was stopped, there was no more deflection in the galvanometer. The deflection came to 0, indicating that there is no production of the current. Now, when we are moving the magnet away from the coil, again children, the galvanometer showed deflection. But children, this time the deflection was in the opposite direction. So this time also in current was produced, current was induced in the coil, but its direction was reverse. Right? So what does it show? What does it prove? It shows that when there is motion, when there is relatively motion between the coil and the magnet, then only current is induced in the coil, current is produced in the coil. But when the motion stops, when there is no relative motion, no current is induced in the coil. So it showed that relative motion between the coil and the magnet is responsible for the induced current in the coil. Now, let's move towards the second experiment. Now, children, your first experiment, the first experiment was that motion is required. There should be relative motion between two. And there we had a bar magnet. So, in experiment 2, what we are doing? We are replacing the bar magnet by another coil which is carrying current. Here you can see battery. Yes, children. So this is a coil carrying current, and this is going to do the same work as the bar magnet did. So here you are having a coil C of few turns of conducting material, and that is connected to a galvanometer, and the galvanometer will detect the presence of current. And here we are having another coil C dash which is connected with a battery, and it is a current carrying coil. Now what we are going to do now, children, when the coil C dash is moved towards the coil C, the galvanometer showed deflection. It means current is induced, current is produced in coil C due to the motion of the coil C dash. But as the C dash stopped moving, as we made the C dash at rest, there was no deflection in the coil. Now children, when we are moving the coil C dash away, again children, there was deflection in the galvanometer, but this time the deflection was in opposite direction. Okay, and children, what they are saying is, on reversing the direction of the current also, on reversing the direction of the current, the direction of deflection in the galvanometer also got reversed. Yes. So the galvanometer gave larger deflection when the coil moved faster away or towards. So the rate of motion, how fast you are moving, how slow you are moving, so depends on, that is also one of the factor on which the magnitude of induced current depends, right? Current ज़्यादा produce होगा if you are moving the coil towards the another coil faster, or you are moving the coil away but at a greater rate, at a greater speed, right? Now let's talk about experiment number 3. Experiment number 3. So experiment number 3, Faraday showed that the relative motion is not absolutely that is required. So current can also be produced without without relative motion. See, for example, here as you can see in this experiment, when your key switch is connected, a key is connected with the coil, that is C dash. So what is happening over here is when you are pressing the key, when you are putting it on. So at that time, when the switch is on, momentarily for a second, the deflection is shown in the galvanometer, indicating that the current is produced in this coil, right? And after that moment, again the deflection, the switch is on, but the deflection comes to 0. That was only for a moment. Now when children you are putting the switch off, initially you had put the switch on, now when you are putting the switch off, again the galvanometer needle got deflected for a moment, but this time it was in opposite direction to the previous one. And as soon as you put it off, it showed a deflection and then again it came back. So it showed the deflection when you were pressing the key on and off, which was for a moment, which was momentarily, and it was in the opposite direction, right? So from here, we can conclude that the cause of induced EMF, what is the cause? Why EMF, why current is produced? So, current is produced whenever what you are doing, when you are bringing the bar magnet near, when you are moving it away, when you are putting the switch on and off, what are you changing? We are changing the magnetic field lines that are cutting, right? The magnetic flux that is passing through the coil. So, what is the cause? The cause is induced EMF is produced whenever the magnetic flux linked with the coil changes with time. So only magnetic flux is present, that is not enough. If magnetic flux is present, no current will be produced. But the magnetic flux must change. Then only EMF will be induced. EMF will be produced in the coil. And the direction of EMF, it depends upon the direction of motion of magnet. We saw when you are moving the magnet towards the deflection, suppose it was in this direction towards left, and when you move the coil away, the deflection was in the other direction, suppose right. So the direction of induced EMF, induced current, it depends upon the direction of motion of magnet.